So back to the pancake example. Suppose we have on hand 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. How many pancakes can we make? Just quick off the top of your head. Yeah, I'm talking about this one. So somebody said 15, which is very good because that is the correct answer. How do we figure that out, though? Because that may or may not be obvious to you. Yeah, we have to look at each of the ingredients and see how many pancakes could we make? Which one are we going to run out of? So the thorough way to do that would be to take the 3 cups of flour, 3 cups of flour. This is your chance to write flour. It's not fluorine, flowering. Here's the flour. We want to know how many pancakes. I'm going to call pancakes PC because I'm tired of writing pancake. And we're going to divide by cups of flour. We can make 5 pancakes for every 1 cup of flour. So that means if we have 3 cups of flour, we could make 15 pancakes. Okay, so that's great. What about the eggs? Well, 10 eggs, and we get 5 pancakes for every 2 eggs, right? So if we had enough of the other stuff, we could make 20 pancakes to use up all the eggs. Yes, thank you. 25. This is testing you. See if you're paying attention. And if you believe that, I get a bridge I'd like to sell you. Baking powder. 4 tisps of baking powder. Don't tell me you never called them that. 5 pancakes for 1/2 teaspoon. You know, fractions are ugly. Let's not write a fraction there. That's 0.5 teaspoons. So 4 times 5 is 20, divided by 1/2 is 40. 40 pancakes. So we came up with 3 different answers. The smallest one is the correct answer. Because let's think about it. Each recipe makes 5 pancakes, right? So we make 5 pancakes, and then we make 10 pancakes, and then we make 15 pancakes. Can we make 20 pancakes? No, because we ran out of flour. You can't make pancakes if you run out of flour. You're done, right? You're done. So the way we figure these things out is we look at all of the ingredients and we calculate how much product we could make, and whichever one is the smallest is how much we can make. Because when we get to that point, one of the things has run out. What ran out? The flour. The flour limits how many pancakes we could make. If we had more flour, we could make more pancakes, but we don't, right? And you always run out of something. So we call the flour the limiting ingredient or the limiting reactant because it limits how much we can make. So here's the picture. There's the flour. If we had enough of everything else, 15 pancakes. The eggs make 25 pancakes. The baking powder would allow us to make 40 pancakes. But we can't make 40 pancakes because we run out of flour first. So in a chemical reaction, we would call the flour the limiting reactant. The 15 pancakes would be called the theoretical yield. Because that means if everything goes perfectly, that's the most pancakes we could make. That's our best scenario, 15 pancakes. You might say, well, what could happen? Well, stuff happens, right? Suppose we cook our pancakes. We accidentally burn 3 of them, right? Because somebody came to the door and we forgot we were cooking pancakes until we smell them burning. Oh, shoot. Nobody in the house will eat burned pancakes because you don't live with my husband. And one of them falls on the floor, and we haven't mopped the floor for a while. And so, yeah, we're not eating the pancake off the floor. The 3-second rule doesn't apply to that. Okay, so we lost 4 of the pancakes. So did we actually end up with 15 pancakes? No, we ended up with 11 pancakes. That's our actual yield. So we actually made 11 pancakes. In theory, we could have made 15 pancakes, but life happened to us when we were making pancakes. And if you have animals and or children, you know that that sort of stuff happens all the time. So that's the actual yield. The amount of product that you actually make, right? The theoretical yield is the amount of product that you could theoretically make if everything worked perfectly. But everything working perfectly never happens. We like to express this relationship as a percent yield. And remember that percent is part over whole times 100, the part over the whole. So in this situation, it's going to be the actual yield divided by the theoretical yield. That should probably be written in there somewhere. I think it shows up later, but not very clearly. This is the actual over the theoretical yield times 100 to make it a percentage. So how much you actually made divided by how much you should have been able to make. And so we find that our percent yield for pancakes today was 73%. Not too bad. Could be worse. Could be like the time that my 2-year-old was helping me. My kids love to bake. It's kind of like chemistry. So he was helping me make pies for Thanksgiving, because I make all the Thanksgiving pies, because I make good pies, and I like pie. So, I'll make the pie, you do all the other stuff. So he was helping me, and we made 2 pumpkin pies, and then I put him to bed, and I went to make 2 more pumpkin pies. And I tasted the crust, which was a really good thing, because normally I like pie crust. And so I tasted the crust, and it was so salty, I had to spit it out. I mean, it was just nasty. And I'm like, what on earth happened? Did I not mix it up well enough? And so I tried a piece from the other side, and that was nasty too. I'm like, oh my goodness, what on earth happened? And I thought, I know I'm tired, but I really don't think I put in that much salt. So then I looked at the flour canister and tasted the flour. My little guy had put salt into the flour canister when we were making the pies earlier. Thankfully, after we had made the crusts for the first pies. And thankfully, there was another bag of flour in the cupboard, and so because you can't go to the store at midnight on the night before Thanksgiving and buy flour. Nobody's open. But yeah, so that happened. So that was about a 67% yield on those pies, because I got 4 out of the 6. So it happens. It happens. So in a chemical reaction, the actual yield is determined experimentally. You actually do the reaction and see how much you get. That's not something you can calculate while you're doing your homework, right? It's not something that you can just pick some number. There's no secret formula for calculating actual yield. That's something that's actually measured. So when we do problems and calculate a percent yield, they're going to give you the actual yield. You can calculate the theoretical yield. So the actual yield is going to depend on the reaction conditions, on the type of reaction, on your skill in the lab, on all kinds of things. The actual yield is almost always less than 100%. And that makes sense, right? If we have enough ingredients for 15 pancakes, could we end up with 17 pancakes? Not if they're all the right size that they're supposed to be. We can't make something out of nothing. Sometimes, in a chemical reaction, the percent yield is greater than 100%. I guess first I should talk about how it's less. Well, it's kind of like with the pancakes. Some of the product doesn't form. Some chemical reactions don't go all the way to completion. They react mostly, and then some of the reactants are just left. That's like if you let the 9-year-old make the pancakes. And she's really enthusiastic at the beginning, right? And then she's cooking the pancakes and she gets bored, right? And so she doesn't finish cooking the pancakes. So they don't all get made. That's one thing that can happen. Product is lost. That's like, burning or dropping the pancakes. You can probably imagine, having spent some time in the chemistry lab now, how you could spill some of your product or make a mistake like that would cause you to lose product. How could it end up being greater? Well, the most common problem is that you're isolating a solid from a liquid solution, and so you filter it out, but it's wet. If you do not allow it enough time to dry and weigh it while it's still wet, then you're going to include the mass of the water with the mass of your product, and it will look like you have more product than you actually do. When you do the calculation, you end up with over 100%. When you get over 100%, that's an indication that something went a little bit wrong. If it's like 120% or something, it's probably just some sort of an experimental problem. Maybe there's a contaminant. Here's another story. Sorry, can't help myself. So I was in a quantitative analysis lab as an undergrad, and we had been working very hard on these. We each worked alone, and we were doing this experiment, and then we had this sample at the end in a crucible, and we were burning off the filter paper. And we'd been working on this for almost 3 hours, and our entire grade was based on our percent yield. And so this is, it's really got to be right. So we're ashing, and a fly. This old building at Iowa State University had windows that opened without screens. And I don't remember if we had air conditioning or not. I kind of think not. So the windows were open. There's flies coming in and out. Not tons, but some flies. Flies over somebody's crucible. The heat kills it. It falls into the crucible. And before we could even really gasp, it's all burned up. And it's like, okay, there's an ashed fly in the crucible. That's going to add some mass to the product. How much mass? This guy, he's like, ah, right? Because he's one of these intense, science geek kind of guys. So what does he do? He's like, well, I need to know the mass of an ashed housefly. So he went around and collected 10 houseflies and ashed them and found the average mass of a housefly and subtracted it from the mass of his product. I really, really wish I could remember how he did on his percent yield. But what has stuck with me is the creative problem solving, right? It was just one of those awesome moments in chemistry lab. Okay. Pardon me?
Now he works for NASA.
He might, actually. Okay, so here's a summary of this. Limiting reactant, sometimes called a limiting reagent, just a different word. That is the reactant that gets completely used up. That's the one you run out of. It's limiting reactant because it limits the amount of product. The theoretical yield is the amount of product you calculate using stoichiometry that you could make based on that limiting reactant. Everything going perfectly. The actual yield is the amount actually produced. That would have to be told to you, or in the lab you would actually measure it. And then the percent yield is the actual yield divided by the theoretical yield times 100. If you end up with a percent yield of 5,742%, then you probably did some of your calculation wrong. If you end up with 103%, check your work, but that might be okay. This section just goes on and on and on. Okay, so let's apply this limiting reactant idea to a chemical reaction. So here we've got titanium reacting with chlorine to form titanium 4 chloride. The question is, what are the limiting reactant and the theoretical yield if you start with 1.8 moles of titanium and 3.2 moles of chlorine? We're going to treat this just like we treated the pancake problem. Here we have 2 ingredients, and we have amounts of 2 ingredients. We're going to take this amount of titanium and find out how much product we can make. We're going to use, this is step one, use stoichiometry to find the amount of product that can be made from each reagent. So we're going to do two parallel calculations, one for titanium and one for chlorine. Then we're going to look at the results of that and find the smaller one. That's our answer for I'm sorry, I think about this a little differently. I should change this slide. The limiting reactant is the one that gives the smaller yield, and the theoretical yield is the smaller yield. I think of it as 132. I find the smaller yield, and then I look back and see what reactant. So let's do this. So I'm going to write the amounts under their formulas, 1.8 moles of that, and 3.2 moles of this. And what I'm trying to find is the moles of product. Sometimes there's more than one product, and then you want to be sure you're calculating the right product. So I'm going to take 1.8 moles of titanium, and I want to figure out how many moles of product, titanium 4 chloride, that could make. So I'm going to multiply by moles of product and divide by moles of my reactant. I do that so these units cancel out. Then I look at the equation. 1 mole of titanium will make 1 mole of this. So this is 1 to 1. Well, didn't really need a calculator for that, did I? That's okay. 1 mole of titanium chloride. And then we do the other one. 3.2 moles of chlorine. Again, moles of product on top, and now moles of chlorine on the bottom. So those units cancel out. We look in the equation. 2 moles of chlorine get us 1 mole of titanium chloride. 1 to 2. So this will give us 1.6 moles of titanium chloride. So we did 2 calculations, we come up with 2 answers, but there's only one answer. It's the smallest one. So you look at the numbers and put a box around the smallest one. That is our theoretical yield. What happens in lab sometimes, it doesn't really matter in mastering chemistry or on the exams, but in lab you might have a problem like this, and a student will put this work down, just what I have up here, and think they're done. And you'll lose points because, yeah, you did some great work, but you didn't finish. What is the answer? So you need to indicate that somehow. Put a box around it and write something. You don't have to write a whole beautiful complete sentence, but show me clearly this is my theoretical yield. And then to find the limiting reactant, we've identified this, just go back. Which one made that? That's the chlorine. So that's our limiting reactant. So we got a limiting reactant and a theoretical yield. Any questions? This was a simpler problem because we're just looking at the middle of that stoichiometry thing, the mole to mole, because we're focusing on the concept of the limiting reactant. You want to do another one like that? Great. So here's sodium and fluorine reacting to form sodium fluoride. If you begin with 4.8 moles of sodium and 2.6 moles of fluorine, what's the limiting reactant and the theoretical yield of sodium fluoride? Well, let's identify what we have. Now, I am writing directly on my problem, but you don't always get to do that. what should you be writing on your paper? You should write the balanced chemical equation, and then you should write these amounts underneath the appropriate formulas. And then the question is, how much of this? Right now, in this section, we're focusing on limiting reactant problems. On the exam, there might be just regular mass problems and limiting reactant problems all kind of jumbled up together. How do you know which is which? If they give you two masses, chances are very good it's a limiting reactant problem. So limiting reactant, we have to do two calculations. So 4.8 moles of sodium, and we use the mole ratio to figure out how many moles of sodium fluoride. I want to divide by moles of sodium. What's the ratio? 2 to 2. So that ends up being 4.8, doesn't it? 4.8 moles of sodium fluoride. Then we do the other one. 2.6 moles of chlorine. We're going to have moles of sodium fluoride. What am I doing? That's not right. There's no chlorine in here. My husband calls that a brain fart. Moles of sodium fluoride, and this is moles of fluorine, not chlorine. And I'm doing it this way so the units cancel out. Then I look at up here. Fluorine, one of those gets me two of these. One fluorine, two sodium fluorides. So I've got two answers. Which is the real answer? The smaller one, 4.8. That's the theoretical yield. What's the limiting reactant? Sodium. The limiting reactant is the one that gets all used up. As we're making sodium fluoride, 4.5 moles, 4.6, 4.7, 4.8 moles, and everything stops because you ran out of sodium. You can't make any more. Questions?